welcome to your next section of Chapter 8. In this section, we're going to talk all about different characteristics of waves. So first, we're going to start by looking at how waves form and their typical formation. So the first step in that is something called a sea. So the sea is the area where the wind-driven waves are actually generated, and sometimes we also call this the sea area. So these waves are actually going to be characterized by choppiness and the waves moving in lots of different directions. So as we go through looking at the formation of waves, I actually want to help keep track for you the steps because you're going to need to know them for your exam. So when we're looking at the formation of waves, we start with the sea. So the sea, the waves move in different directions, and it's really choppy. So before we go into parts 2 and 3, we're actually going to talk about what affects the wave's energy, because that's going to lead us into those last two steps. So the factors that affect wave energy also affect the height of the wave. So this slide says wave energy, but it could also say wave height. So the three factors that affect wave energy and wave height are wind speed, which is just the speed of the wind duration, which is the length of time that the wind is blowing in one direction, and then fetch, which is the distance where that wind is blowing in one direction. So for your exam, make sure you know that wave height depends on these three factors. So wave height depends on wind speed, wind duration, and fetch. So again, wave height is directly related to wave energy. So in that sea area that we just drew and talked about where it's choppy, the waves are usually less than 2 meters or about 6.6 feet. And what happens in this area is as that sea waves in the sea area gain energy, their steepness increases. And then when their steepness reaches that value where we talked about when the steepness is greater than 1/7, they break and form ocean breakers that we call whitecaps. Also, what's really interesting is they have a scale called the Beaufort Wind Scale that actually will describe the appearance of a sea surface, and then based on the appearance will tell you what the approximate wind speeds are. So continuing to talk about wave height, we're going to look at how high waves can actually be. So there was a ship, the USS Ramapo in 1933, that got caught up in a Pacific typhoon. And they were actually able to measure waves accurately because they were traveling with the waves. So when they took the measurements of the waves, they found that the waves were 34 meters or 112 feet high. And this was really important because before these measurements, it was thought that waves couldn't exceed 60 feet high. So they actually learned a lot from being caught up in that typhoon. So a lot of ships are damaged or disappear annually due to high storm waves. Luckily, the USS Ramapo was undamaged. But other boats haven't been as lucky. So this picture shows you an aircraft carrier, the Bennington, that was damaged by high waves in 1945. And you can see just how their runway was just completely smashed and collapsed under the force of the waves. So waves are really strong and have a lot of energy. So we're getting back to that typical wave formation. Remember, we start with that sea, and they actually call it a fully developed sea when the waves can't grow anymore. And that's because they're losing as much energy in breaking as they're gaining from the wind. So this is that choppy area again where the waves are forming due to the wind. And then the second part of wave formation is called the swell. And in this case, we have uniform symmetrical waves that are traveling outward from that storm area. So basically, as those waves in the sea area move towards the margins where the wind speeds are diminishing, the waves move faster than the wind, the steepness decreases, and those waves become those long crested waves. So if we were going to move on from our sea to the swell, our swell would look more like this. And moving in one direction. So now they're uniform and they're going in one direction versus the C where they're going in many directions. And then we have a final step, which we're going to get to in a couple of slides, but I want to mention it now, called the surf. So the surf is that near shore area where you would surf the waves and where they're breaking. So it's not really easy to draw a breaker, but imagine that spilling over. And these are breakers near the shore. So for the exam, all you need to know is the typical formation of waves goes from a sea to swell to surf, and just identify that in a multiple choice question. You just need to know this order. So looking a little more at swells, remember they have those long wavelengths in their uniform. Well, eventually those long wavelengths will travel faster and outdistance other waves. So then we have some different characteristics and some terms that we need to talk about. So a wave train is when you have a group of waves with similar characteristics, and this is the one that we're really going to focus on. So as a group of waves leaves the sea area and becomes a wave train, which again is the group of waves with similar characteristics, that leading wave will keep disappearing, but there's always going to be the same number of waves in a group, because as that leading wave disappears, a new wave will actually form and replace it at the back of the group. So if we're looking at this image that kind of shows you how the wave trains work. So here's your leading wave, wave 1. Again, this is your wave train. So group with similar characteristics. You can see they have the same wave heights and wave lengths. So wave 1 is your leading wave. Well, here in the second image, you see wave 1 is dying out, but wave 5 has replaced it in the back. So now wave 2 is your leading wave. When wave 2 dies out, wave 6 replaces it in the back. Same thing again, wave 3 is your leading, wave 3 dies out, and wave 7 replaces it in the back. So those waves always are replacing themselves, and what's important to note is that as each wave disappears and a new one comes in the back, the entire wave train has moved forward. So while we talk about characteristics of waves, we're actually going to talk about some abnormal waves that you've probably never heard of, and these are called rogue waves. So rogue waves are massive, spontaneous, solitary ocean waves, and they reach enormous heights and occur at times when the normal ocean doesn't have a lot of big waves. So sometimes rogue waves are also referred to as super waves, monster waves, sleeper waves, or even freak waves. So they're really just individual waves of exceptional heights or abnormal shapes. They've been popularized a lot in movies like The Perfect Storm. I'm actually going to show you a picture of a luxury liner, the Michelangelo, that was damaged from a rogue wave in the North Atlantic in 1966. So in this image on the left, this is the view from the Michelangelo as it's crashing through that rogue wave. And then the picture on the right actually shows you the damage after it gets hit by that rogue wave. So this red oval, you can see a chunk of that boat has actually disappeared. It's a missing section. And you can just see the damage up top as well. So rogue waves are really difficult to forecast. And that's because typically they occur where there's strong ocean currents that are going the opposite way of the waves. So that's kind of what that last bullet says, where it says strong ocean currents amplify opposing swells. That's all it means. So if you look at the image, it's where these storm waves are moving in an opposite direction from the surface currents. So for the exam, you just need to know where rogue waves tend to occur, and they tend to occur where storm waves move against strong surface currents. Now, when we finish up this section, we're going to kind of finish up talking about what happens to waves as they approach the shore. So there's a lot of physical changes that occur to a wave as it moves from deep water into shallow water. So basically, as that deep water wave becomes a shallow water wave. So some of the things that happen are wave speed decreases, and that's because the shallow depth interferes with that circular particle movement at the base of the wave. Also, the wavelength decreases, and that's because as one wave is slowing down, the one behind it gets closer to that wave that's being slowed down. The wave height increases, and that's because that wave energy has to go somewhere, so it goes up. And the wave steepness increases because the wave height increases and the wavelength decreases, which all causes that steepness to increase. So for the exam, make sure you know the information on these slides to basically know these bullets, but pay special attention to wave height. So really know that as waves approach the shore, the wave height increases. So this is an image of the processes that occur on the previous slide. So out here's our deep water waves. You can see the waves are constant. You can see the wave base. Now as these waves are coming into the shallower area, you can see they're touching and feeling the bottom now. Their wavelength is shorter, their wave heights are increasing, and eventually they're breaking. So since we talked a little bit about breakers, I'm just going to finish that up in this section. It's a little preview to your next section. So breakers, basically what happens is that surf starts as swell from distant storms. So we looked at sea, swell, and surf. So the surf starts as that swell moving in, but as they get closer to shore, the waves actually begin to break. And the surf is generated by the local wind, so that's what makes it choppy, have a lot of energy, and also be unstable. So the breakers that occur in the surf zone or the near shore area are actually shallow water waves. And in the next section, we're going to talk about the different types of breakers and wrap it up by talking about tsunamis. So make sure you continue on with that last section of chapter 8.